Up until now, every one of our questions has required us to imagine that there were no deposits or withdrawals made in the bank account during the relevant time period, or that there were no changes in the interest rate or in the compounding frequency. In reality, though, this does sometimes happen. So we're going to look at two more difficult questions which involve situations in which we have to consider our answer in phases. In the questions that we're going to look at, we're going to have to calculate the final amount in a bank account up until a certain point in time. At that certain point in time, a fundamental change will occur, which will then require us to have to begin a new analysis of compound interest. And when that fundamental change occurs, the amount that's accrued in the bank account will then become our new principal. Think about it on a timeline. We have our prior amount, and then at a certain point we have an after amount. Well, when that phase ends and the next phase begins, the after amount of phase 1 becomes the prior amount of phase 2. And then we have to calculate under new circumstances what will be the final amount at the end of phase 2. So, fundamental changes that require us to let A become P and thus begin a new phase in our solution include a deposit, a withdrawal, a change in interest rate, or a change in the compounding frequency. You're probably hoping for an example to make this a little more clear. We have two examples for you. Example number 1. When Simon was born, his parents invested $1,000 in an account that pays 4.4% per annum, compounded quarterly. Okay, very generous of them. Then on Simon's 6th birthday, his parents deposited an additional $1,000 in the same account. We're curious how much will be in the account on Simon's 18th birthday. So there have been two deposits. Well, the way we do this is as follows. We start with phase 1. Phase 1 lasted 6 years because a deposit was made on the day he was born and nothing changed until his 6th birthday 6 years later. So during that phase, the final amount is unknown, but the principal was $1,000. Little letter I was 0.044 divided by 4, since the compounding rate was quarterly, which was 0.011. And little letter n was equal to 6, the number of years, times 4 because of the quarterly compounding frequency, which became number 24. So we plug these numbers into our formula, a equals p, 1 plus I to the n, and we evaluate our bracket first, and then we evaluate our power with the exponent. We get 1.300252661, and our original principal was 1,000, and so we get a final amount of $1,325 on Simon's 6th birthday. Now, when he woke up in the morning on his 6th birthday, he's only 6 years old, so he probably didn't know this, but he actually had $1,300.25 sitting in the bank. Well, we begin phase 2. The final amount is unknown, but now the principal becomes, for the next 12 years, the principal will be the $1,300.25 that he had in the bank the morning he woke up, as well as the $1,000 that his parents deposited later that day. He woke up in the morning of his 6th birthday with $1,300.25 in the bank, but he went to bed that night with $2,300.25 in the bank because his parents deposited another $1,000. This is our new principal. Well, this principal will apply for the next 12 years because we're curious about how much he has on his 18th birthday. Little letter I is 0.044 divided by 4, which is 0.011, because of our annual interest rate and our compounding frequency, which is quarterly. And n is 12 times 4, which is 48. 12 years, because we're going from his 6th to 18th birthdays. So we plug these numbers into our formula, $2,300.25 times 1 plus 0.011 to the exponent of 48. Well, we evaluate our bracket, we evaluate our power, we multiply 1.69065685 times $2,300.25, and we get $3,888.93, which means that Simon will have $3,888.93 on his 18th birthday, and maybe he can use that to college or go to Cancun. Who knows? Okay, the next question talks about Marguerite. Marguerite invests $2,300 in the bank at 3.6% per annum, compounded semi-annually. So 3 years later, she hasn't done anything with it. The bank phones and lets her know that the annual interest rate is the same, but her compounding frequency is now monthly rather than semi-annually. This might happen sometime. So we want to know how much money will be in her account 5 years after this change. Well, we have two phases. The first phase lasts for 3 years, and it involves 3.6% per annum compounded semi-annually. And then the second phase will be for 5 years at 3.6%, but now compounded monthly. So we go back to our question and we figure out phase 1. We don't know our final amount in phase 1, but we know that we began with $2,300. Her annual interest, her little letter I will be her annual interest rate divided by 2, because in phase 1 it's semi-annual, which is 0.018. Then little letter n will be the number of years times 2, which is 6. Phase 1 only lasts for 3 years. And so we can see that at the end of phase 1, following our normal compound interest steps, we have a total amount of $2,559.85 sitting in the bank. At this point, we have to now consider that $2,559, which occurred at the end of phase 1, to be the beginning of phase 2. Our amount is unknown, and our little letter I is now 0.036 divided by 12, because we've now gone to monthly compounding, which is 0.003. This monthly compounding lasts for 5 years, so our little letter n will be 60. We plug these numbers into our formula, and we get that our final amount will be equal to $2,559.85 times 1.003 to the exponent 60. 1.003 to the exponent 60 is 1.196894803. We use a lot of decimal places because we want to be accurate to the penny. So our final amount in the bank is $3,063.87. So we make a therefore statement. Therefore, Marguerite will have $3,063.87 5 years after the change in compounding frequency.